All right, this is Roki bringing to you 2K graphing functions as well as 2L finding where graphs meet. So when we draw any graph, because we're starting to see more and more different types of functions as we move along here, we always want to have the following features. We need to have the axes intercepts, both x and y, if they exist. We need to have any turning points, which could be a max or a min. For us, for right now, that's probably only going to be with parabolas. Later on in the course, we'll be able to use calculus to find maxes and mins for other complicated functions by hand. Otherwise, we'll be using technology to find them for now. Any values for which the function does not exist, more on that in a moment, and also any asymptotes, which we talked about in the rational function section. That'll be the same idea here. When we talk about values for x where the function does not exist, you need to think about these things algebraically. You can't just rely on your calculator. I'll give you an example here. What does this graph look like? X plus 2 times x minus 2 over x minus 2. Well, I mean, if you think about it, you should just be able to cancel x minus 2's, right? And you should get a graph that looks just like the line x plus 2. Except we know from the equation that x could not be equal to positive 2, right? Couldn't be, but it sure looks in this graph like it's filled in everywhere. Let's check a table. Menu, table, here it is. Oh yeah, you know, when x is equal to 2, this graph happens to be undefined. So the calculator is not going to show you the hole that is in the graph. You would be responsible for showing that on paper. And I think we've talked about this before, but just in case, you draw your line, and we would just draw a little hole like that when x is equal to 2. Let's just make sure we're good with our calculator skills. I'm going to do letter B here. This is a pretty nasty looking quartic function. I am definitely not going to do this by hand. So let's just work out, well, parts of it I can do by hand. The rest of it I'm going to have to work out with a calculator. So find the axes intercepts. Well, the y-intercept is easy. That'll be when x is equal to 0. I can tell that that's going to be 2. And finding any x-intercepts, that's going to be tough to do by hand. I can't just set this equal to 0 and solve it. So let's go to the calculator. I've already graphed it. We just want to find out. Looks like there's only 2 of them here. So I'm going to press menu, analyze graph, find the zeros. There's 1. And I'll do it again. Menu, analyze graph, find a 0. There's another. So my 2 zeros will be negative 4.97 and negative 1.55. 3 significant figures each, of course. Next, find any turning points. There looks like there are a few. It's clearly one here, and there's going to be one down here someplace. So I'm going to, again, analyze the graph. Let's find the maximum first. Right there, okay. The turning point, that's going to have both an x value and a y value. So we have negative 0.805, 2.97. Negative. I forgot what it was. 0.805, 4. 2.97. Next for the minima. This one looks easy. Oh, that ended up just being the y-intercept, so 0, 2. And the other one, let's see if we can grab it without having to change my window. I'll make my lower bound here. Excellent. As long as I press enter, it gives me one, and it's going to be negative 3.88 and negative 33.5. Okay, let's jot these down. Okay. So my other turning points, put my minima in green here. That was negative 3.88, negative 33.5, and my other minimum was at 0.2. Okay, asymptotes of the function. This function has no asymptotes. It is clearly defined for all values for x. Well, at least within that domain it is. And yeah, it'll be okay, asymptotes. Okay, asymptotes. This function has no asymptotes. Clearly, certainly within this domain, it's defined for all values of x, although as a polynomial function, it's going to be defined for all values of x, no matter what my domain was. So there's no vertical asymptotes, and there will also be no horizontal asymptotes, because as x gets really, 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 really big, this is just going to go to infinity. I mean, this is a really, really big number to the 4th power. It's going to be huge. Also, as x gets really, really big in the negative direction, I'll have a negative number raised to the 4th power. So that'll be a super, super big number. So it's going up to infinity in both directions. So it's not going to have a vertical asymptote either. So there actually are none here. Okay, state the domain and range of the function. So since we know that it has no vertical asymptotes, and likewise there's no other values where x is not defined here, this is the domain. The domain was already given to us, from -5 to 1. For the range, well, I just said that it's going up towards infinity as x gets larger in both directions. Now that's true, but that does not mean that my range should be y is greater than or equal to some number, and that y just goes from that value up to infinity, because we're actually trapped here in between -5 and 1. So I'll never actually make it to infinity. We have specific places where the function ends. In order to work out the range, I'm actually going to need to sketch the function first. So the endpoints, it turns out that the y value for -5 is 2, and the y value for 1 is 12.8. So using that and the general shape of the graph that I saw on the calculator earlier, I can kind of sketch this thing. It's going to look something like this. Okay, so this will be -5, 2. This will be 0, 2. This point up here can be 1, 12.8. We had this max, which was -0.805 and 2.97. We had this minimum down here, which was -3.88, -33.5. Oh, and then we had the two x-intercepts, which were at -4.97 and -1.55. And there you go. That's all the important points for this function on a sketch. It doesn't need to be drawn very pretty at all. Just make sure that you have all the important pieces of information on the picture. All right, so now let's look at letter C, which is going to be notably different. Got it started on the calculator already. All right, so strange looking graph. Let's see if we can sketch this on paper and figure out all the important parts to it. For starters, axis-intercepts should be able to do that by hand. Y-intercept, when x is equal to 0, the y value is going to be -2 divided by 16. So that's -1/8, or If you want it as a decimal, it'll be negative 0.125. As for the x-intercepts, we need to set that numerator equal to 0. That is not factorable, but using the quadratic formula, you can work out that the x values will be plus or 2 plus or minus the square root of 6. As decimals, those would be negative 0.449 or 4.45. Turning points of the function, we'll use technology for this. Certainly there's a maximum staring at us already, so I'll analyze the graph, find the maximum. By the way, there's another way to do this. You don't need to use the touchscreen to scroll around. You can also type in values. So again, it's asking me for my lower bound. This point, I don't know what that x value is, but it's clearly bigger than 0, so I can just type 0, press enter. And then for the upper bound, well, I know that whatever point that is, it's less than 10, so I'll type 10, press enter, and it gives me the value. This is definitely faster for you to do on a handheld calculator. For me, since I'm doing this on my computer, I'm never going to do it that way. It's faster for me to just use my mouse and go through it that way, but shortcut for you. Anyway, I got a max here at 5.3, so let's note that. Okay, is there a minimum? So the question now is this going to connect down here and come back up? I could start scrolling down. It doesn't really look like it. Can I be sure? Well, I can't really be sure without calculus, unfortunately. But we can be pretty sure in this case that there won't be, because we just look at the function, and I notice that there should be a vertical asymptote when x is equal to 4. So we're going to say that there's no minimum going down there. And that brings us to part 3, the asymptotes. So yeah, there's a vertical asymptote when x is equal to 4. Is there a horizontal asymptote in this case? Yes, definitely. And we're going to work it out the same way as we did with the simple rational functions in a previous section. In this case, if I were to rewrite this as x squared minus 4x minus 2 over x squared minus 8x plus 16. Again, so when I think about what happens when x gets really, really big, right, as x goes towards infinity, what's happening to the y value here? I don't really care about -2, right? If I subtract 2 from some really big number, it really doesn't matter. I also don't really care about the 16, so I can ignore those. And in fact, I can actually ignore the second terms as well, because when I take the really, really big number and I square it, then I'm going to have a really big number. So subtracting away 4 times that original big number is just not going to impact my super, super big number now. In general, when we do this, we want to just look at the highest degree power of x in both the numerator and the denominator. So in this case, it's just x squareds for both of them. I can ignore all the other terms. So as x gets really, really big, y is getting closer and closer to just 1, because this is 1x squared divided by 1x squared. And likewise, as x gets really, really small, or really, really big in the negative direction, I should say, y is also going to tend towards 1, because I'll have a negative number squared divided by that same negative number squared. You can have, of course, multiple horizontal asymptotes. You might notice in now, there's no guarantee that the horizontal asymptotes will always be the same as x goes to plus and minus infinity. Sometimes they can be different, so always check them both. Anyway, horizontal asymptote will be y equals 1. State the domain and the range of the function. So in the previous example, we were kind of given the domain ahead of time. Here we're not, so is x defined for all values? No. But it is defined for all values except for 4. And again, the range because I don't really know what this function looks like, I should probably check the graph before just assuming anything. So let's just double check here. Okay, so the maximum value is 3, and it's going to be defined for every value less than 3 because we're getting closer to this vertical asymptote as we go farther and farther down. So my range will be y is less than or equal to 3. And we're going to sketch the graph now and show its key features. There are my axes. And again, I'm just going to draw the two asymptotes, and then I'm going to just write in the general shape that I saw from the calculator. Arrows. Like this. Now, this is okay. We are allowed to cross over an asymptote. An asymptote does not mean that the function is never equal to it. An asymptote means that a function eventually gets closer and closer to that value, but never touches it. So this is an asymptote at y equals 2 because of what's happening way out here to the right and way out here to the left. It's totally okay to cross the asymptote infinitely many times as long as voice crack. It's totally okay to cross an asymptote infinitely many times as long as the end behavior as x goes towards positive or negative infinity, the y value eventually asymptotically approaches a particular value. So we've got that, and then we're just going to put in all the numbers that we got earlier. So I've got an x-intercept at negative 0.449. I've got an x-intercept at 4.45. We have a y-intercept at negative 0.125. We have a maximum at 5.3. And I should label my asymptotes, shouldn't I? So this is y equals 2, and this is x equals 4. And there you go. That's a crazy looking function, but that's how to graph it. Okay, so there isn't too much of interest in section L, finding where graphs meet. We've already talked about finding the intersections on calculators, but we'll just do one problem here. So here's a graph of f of x is this random function over here on the right. Part A, copy the graph. Okay, I've already got it copied. And on the same set of axes, draw the graph g of x equals negative 1. So that's just going to be from negative 5 all the way to 4. We're going to have a horizontal line at negative 1. Okay, easy. Hence, one of my favorite IB words. Hence, so using the answer from the previous part, state the number of solutions of f of x equals g of x. Well, clearly, there's only one in this case. However, and this is where we can actually do at least a little bit of thought here. Let's say that h of x was equal to k. So k is just some real number. So the graph of h of x equals to k is some horizontal line. Could be anywhere, though. Where does the equation then f of x equal to h of x have 3 solutions? Is there anywhere where it has 3 solutions? Well, yeah, I can see it right there, wouldn't it? So that would happen whenever the k value was greater than 0, but also less than 1. If it's equal to either of those values, then we can see that we're going to have 2 solutions. And actually, that's the next question. Where will there be 2 solutions? And I think it should only be at those particular values. So k equals 0 or k equals 1. Because if I go outside of those boundaries, as I start to go above k equals 1 or below k equals 0, I only have one solution. So part 3, where is there one solution? When k is less than 0, there's certainly only one, but I need to be careful. I can't choose any number less than 0. I can only go down as far as negative 3. And likewise, k can be greater than 1, but it is going to be bounded by 8. Oh, and actually, it can be equal to those two. And finally, for no solutions, that's going to be k is greater than 8 or k is less than -3. Not too tough. Anyhow, that's the end of chapter 2. Rocking and rolling right along. Onward to exponentials.